I want to start with our results first. So we found that in a world with a less than 2 degrees Celsius warming, we are likely to have reached the energy capital stock around 26 or 29. And I should be a little bit more clear here, that is the energy capital stock. So we will have built all the power stations, which will bring us to a 2 degrees Celsius scenario around 26, 29, with a little bit of variation in 2018, 2048. And I'll come to the results, how we got there in a little bit. But basically, new science and new economics have motivated and also informed our approach and research. One was that peak warming is best proxied by the cumulative carbon emissions and not by carbon emissions in a given year. And also that existing infrastructure, and like I said, we were looking mainly at the energy capital stock, but the future emissions of this infrastructure will already use up or consume up a huge part of the budget we have left for 2023. So it makes a lot of sense to look into the committed cumulative carbon emissions, short CCCE. And if these committed cumulative carbon emissions of energy infrastructure will grow over the next couple of years as they did in the last 50 years, then we will have reached the 2 degree capital stock in this sector at least pretty soon. We also looked at sensitivities, and given the short time frame, the rate of the growth of these committed emissions as well as the realized emissions pathway, so what we are actually going to emit over the next 10 years, is not so relevant, or it's not so decisive about the commitment year and the commitment date as is the assumed lifetime. And I'm especially happy that Professor Sokolov is here today, which published a paper together with Davis last year on which we based a lot of our work and which informed a lot of our work. And finally, and that's the reason why this is relevant for today, if the current development of CCS technology continues as it did in the past, so basically non-existent, then we investors might want to pay closer attention towards the possible stranding of assets in the sector. Once we reach that 2 degree capital stock, that will be the only way to actually then achieve the 2 degrees Celsius. So, first of all, what informed and motivated our research? The new science, relatively new science, that it's the cumulative carbon emissions over time, since the very beginning of emissions, which will in the end decide the peak warming. So not the emissions in 1 year is relevant, it's the overall emissions over the entire lifetime of humanity, if you want, which will decide peak warming. The second was that these total cumulative carbon emissions are already determined in a large measure today by the installed capital stock. So all the infrastructure we have today will continue to emit carbon over the next decades, and the cumulative carbon this already commits to today will be very, very important to peak warming. So the question we asked ourselves was, so when will we have actually built the energy infrastructure capital stock, which will bring us to this 2 degrees Celsius? So if we look today, or basically 2014, first thing we did was we updated the IPCC carbon budgets for different warming scenarios and found that in 2014, for a 50% chance to stay below 2 degrees Celsius warming, we have around 320 gigatons of carbon left as total budget we can emit in the future. How would that look like? So the blue line you see here is the remaining budget. The blue line is the historical emissions, and the green line, that's in the future the budget for every year which we will have left if we follow the RCP 2.6 scenario. Oh, sorry, that should have been here. So that's the RCP 2.6 scenario. So we have the historical emissions, and we have the forecast for the RCP scenario. If we look at the same time at committed cumulative carbon emissions from energy infrastructure, we have a simplified historical pathway here that's based on the paper I mentioned from Davis and Sokolow, which was growing at 4% per year since 1950. If we assume that trend continues in the future, that would be the forecast. In that case, we would meet the remaining budget in 2031. However, the forecast is the entire budget. We were looking only at energy infrastructure, so obviously we have to change that forecast a little bit. Because there will be a lot of other sectors emitting in the future. That's just for one of the many scenarios we were looking at. There will be emissions from land use change, industry, from residential, so buildings, transport, and also other energy supply. So we need to account the overall budget left for all of these factors. And if we then look only at the remaining generation budget, so this is basically what is left in 2014 for only electricity generation, given the other future emissions of other sectors, then we see that for different scenarios, for different warming scenarios, we are already basically above that with our committed emissions, for at least for the 1.5 degree world. And for 2 degrees Celsius, there's not much left. And if we look again at the graph I showed before, the purple line you see here, that's basically still RCP 2.6, but this is just the budget which is left to fossil fuels in industry. And in that scenario, we would meet that budget in 2028. But again, there are still emissions, future emissions from transport, from buildings, from industry, etc. So we had to even further refine that. And unfortunately, the RCP 2.0 or the RCP scenarios given by the IPCC, they don't have that granularity. So what we had to do was move away from the RCPs and go to the AR5 scenarios. So there's a huge database with more than 1,000 different scenarios and different granularity. But they're all tested and peer-reviewed from the IPCC. So what we basically did, we looked at scenarios which have the required granularity and which are consistent with a 450 ppm, so 2 degrees Celsius objective. And another very, very important feature I should mention here is we only looked at scenarios which meet that 2 degree objective, but without CCS. Because CCS, it's basically the message of our paper, but without CCS, that would be the message. So looking at these scenarios, we would see the lines here, and we looked at a range of scenarios which are all consistent with the 2 degrees objective, and then came up with estimates for the year when we would meet these budgets in a minimum, maximum, average, and median scenario. What it basically means is, for the minimum, for example, if that is basically a scenario which will meet the 2 degrees Celsius objective, but from this range of scenarios, it's one with very low emissions, whereas this one would be one with higher emissions, but still meeting this objective. And basically, and that's the results of our paper. If the whole world would be to follow a scenario which will bring us to 2 degrees Celsius, but with relatively high emissions in that range, we would commit to the energy infrastructure emissions in 2018. If it was a little bit lower, sorry, that doesn't work. Okay. Then so in the minimum, it's not on the graph anymore, but in the minimum case, it would be 2048, and most likely sometime between 2026 and 29. So what that basically means, and sorry if I'm not, it's a little bit unclear with the formulation, but if all sectors would follow a very, very low emissions scenario over the next decades, then still we would commit to a 2 degrees Celsius energy infrastructure capital stock in 2026 to 29. So I'm not sure how much time I have left.
About 8 minutes.
All right. So I just want to quickly describe how we came up with that findings. So we used a number of publicly available and proprietary databases. For example, we used the Platts World Electric Power Plant database and the Carbon Monitoring for Action (CARMA) database. It's basically the same databases which have been used in the original paper on which Beska worked from Davis and Sokolow. But we also looked at the Global Carbon Budget database to update the carbon budgets and also the different IPCC databases. And what we basically did was first updating the carbon budget, because the latest available estimate from the IPCC was from 2011. So we used the global carbon budget data to update this. And then estimating the electricity generation budget. So how we did that was using the IPCC data sets to come up with different scenarios for the other sectors other than electricity generation, what they might emit over the next decades. And then we used the forecast from the paper I mentioned before for the cumulative carbon emissions from the generation capital stock. And then basically over years, every year you have to update the budget with the forecasted emissions from all sectors and then compare it to the committed emissions in that year from the energy infrastructure sector until these two lines cross, as you could see in the graph. So looking at sensitivities, there are a couple of assumptions we made about which probably there could be a lot of discussion. For example, which realized emissions we took. So over years, what did we assume would be realized emissions to update the carbon budget, but also which future scenarios for the other sectors we use. So and of course as well, with which rate will the committed emissions grow over time. So we did look at the sensitivities for all of this, and this is basically that's the graph I showed before, just in another depiction. If you look at different lifetimes, so how long will existing assets emit carbon, then this is our highest sensitivity, because let's say I think currently the average lifetime of a coal power station is 39 years. If you change that assumption going forward by 10 years, that has a huge impact on when we will have actually commit. So basically, how much do we already commit today, and when will we have committed to the 2 degree? But given that the commitment year is in a relative close future, or a relative near future, for example, realized emissions. So you see here 4 different RCP scenarios and the committed emissions, and it doesn't really matter which of the scenarios, the 8.5, which is really high, or the 2.6 we assume, because it's in the very, very near future, it doesn't really affect the year a lot. And the same holds true for different growth rates of the capital stock. So I think over the last 50 years, the infrastructure committed emissions, they grew by 4% per year. That's what we also assumed going forward. But if you assume 3% or 5%, that doesn't really change the year a lot because of the very near term we're looking at. Finally, discussion, and I think I'm a little bit ahead of time even. Didn't think I would be. But I guess probably I'm rushing a lot. But all right. So first of all, that's probably most relevant to this value. If we had to meet the 2 degrees Celsius goal, asset stranding is very likely. Like I said before, with this very, very optimistic assumptions we make, which is all the other sectors, transport, industry, residential, will follow very, very, very low emission pathways, which leaves a lot for energy infrastructure. But even with that very, very optimistic assumption, we would hit the cut-off date for every investment in polluting energy infrastructure pretty soon. Given current investment plans around the world into coal and gas, And given the current state of CCS, it's very unlikely that we will stop investing in polluting infrastructure in the next 10 to 15 years. But if that happens, or if we keep on investing after that, and we are to meet the 2 degrees Celsius goal, then an asset stranding is very likely. It's almost impossible to avoid. So that should be something investors have on their agenda. Another very important point is, and that's basically last year, so I say only the early retirement of existing and future infrastructure can buy more time to reduce net emissions to the polluting factor to zero. What I mean by that is we saw the highest sensitivity of our result was in the assumed lifetime. If I reduce lifetime of existing infrastructure by 10 years, for example, that would buy us a lot more time. The only question is if I retire this infrastructure early, with what will I replace it? And basically a very popular movement, which is the coal to gas switching, that might actually not be helpful. And why is that? Because if I replace a coal plant, which has only a remaining lifetime of 10 years, by a gas plant, which has a new gas plant which has another lifetime of 40 years, then the cumulative emissions of these two the gas switching might not help in the long term. So it will maybe reduce emissions over the next years, but the cumulative emissions from that will not help. So that's an important feature of our results. And the last thing is, and then I'm done. It seems to be a big push on polluting energy infrastructure appears necessary. And I'm quite honest, there needs to be a lot more research done, because it might even be beneficial if for some of the existing assets, the lifetime is extended even, instead of building new polluting assets. So there needs to be a lot more research what that would actually mean to the cumulative carbon emissions. But what it says for sure is that if we retire some of this existing infrastructure early, we need to make sure that it's replaced by something non-polluting, because otherwise we won't help the whole climate. And that's it from my side. I think we have now some time for clarifying question and then discussion later.
Thank you.